Hello everyone, and welcome. I'm excited to have you here today. Today, we're going to explore the fascinating world of database management systems. This is the first slide, which is our cover slide. As you can see, the title is Information Management Unit 3, Database Management System. We'll briefly go over what this presentation will cover, including key concepts, components, and how databases are managed effectively. Let's get started and dive into this important topic together. Let's take a closer look at some fundamental components of database systems, starting with Data Mart, which is a smaller, specialized subset of a data warehouse designed to serve specific business needs. Moving up, data warehousing itself is a key concept. It's about collecting and managing large volumes of data from various sources to support decision-making. Then we have Data Query Language, or DQL, which allows us to retrieve data efficiently, and SQL data types, which define the kind of data we can store, like integers, strings, or dates. Query processing is the process of interpreting and executing these queries, ensuring we get accurate results quickly. The relational database model is one of the most widely used, organizing data into tables with rows and columns, making data easy to access and manage. Understanding various database models, such as hierarchical or network models, helps us choose the right structure for different applications. A diagrammatic representation of the process of a DBMS helps visualize how data flows through the system, from storage to retrieval, highlighting the interactions between components. Linked files and direct file structures are methods of organizing data at the file level, impacting how quickly we can access that data. Moving to data warehousing specifically, its components include data sources, ETL processes, storage, and access tools. The architecture or structure of a data warehouse supports these components, facilitating efficient data analysis. Features of data warehousing, like data integration and historical data storage, make it a powerful tool for strategic decision-making. Reasons for concurrency management are crucial. When multiple users access the database simultaneously, proper control prevents conflicts and maintains data integrity. Data manipulation language, or DML, includes commands like insert, update, or delete, enabling us to modify data as needed. Structured query language, or SQL, is the standard language for interacting with relational databases. A pictorial diagram of query processing helps us understand the steps involved from writing a query to getting results. Aggregate functions, such as sum or AVG, allow us to perform calculations on data sets efficiently. The advantages of a database management system include improved data sharing, security, and easier maintenance. SQL commands encompass a wide range of operations, from creating tables to complex queries. The hierarchical database model organizes data in a tree-like structure, which is useful for certain types of applications. The role of a database administrator is vital. They oversee database design, security, and performance. Steps in query processing involve parsing, optimization, and execution, ensuring we retrieve the right data efficiently. Basic database concepts include data, metadata, and the importance of data integrity. Accessing records efficiently is essential for performance, especially in large databases. Object-oriented database models integrate data and application logic, supporting complex data types. File concepts refer to how data is stored physically, impacting performance. Types of database models, like relational, hierarchical, or network, offer different ways to organize data to suit specific needs. Components of a DBMS include the query processor, storage manager, and transaction manager, all working together seamlessly. Various file structures, such as indexed sequential files, optimize data access times. Content, in this context, encompasses all these elements that make up the database environment. Understanding these key points helps us grasp how databases function as the backbone of modern information systems, supporting everything from simple data storage to complex data analysis. Let's start by exploring some fundamental concepts of data storage and analysis. We'll look into different types of systems used to manage data effectively. First, there's data warehousing and data marts, which are crucial for consolidating large volumes of data for analysis and decision-making. Next, we have an introduction to structured query language, or SQL, which is the standard language for managing and manipulating relational databases. Moving on, I'll explain relational systems, which form the backbone of most modern database applications. These systems organize data into tables with relationships, making data retrieval efficient and straightforward. We also have RDBMS, or Relational Database Management Systems, which are software that manage these relational databases, ensuring data integrity and security. Additionally, we'll touch on hierarchy-based systems, known as HDMBS, which organize data in a tree-like structure, useful for certain specialized applications. Managing multiple data accesses simultaneously is critical, so we'll discuss concurrency management, which ensures that data remains consistent even when many users are accessing or modifying it at the same time. Further, I'll briefly explain how queries, requests for data, are processed within these systems, allowing us to retrieve exactly what we need efficiently. Lastly, we'll overview network-based systems, called NDBMS, which organize data across interconnected nodes, supporting complex and distributed data environments. Finally, at the core, we have the general concept of a database management system, or DBMS, which is the software that provides a systematic way to create, retrieve, update, and manage data. All these concepts are interconnected, forming the foundation for effective data management and analysis across various systems. Let's take a closer look at what a file actually is. Essentially, it's a collection of records of one specific type. For example, think about an employee file that contains all the details related to an employee. A file is made up of data that is logically grouped together to serve a particular purpose. Now, within that file, we have individual records. A record is usually a collection of data elements that describe a single entity, like one employee. It's a way to organize information about that entity in a structured manner. To clarify further, a record is essentially a logical collection of characters that represent all the details about that entity. And within each record, there are data elements or fields. These are the individual pieces of data, like an employee's name, ID number, or department, that make up the record. So, in summary, understanding these concepts helps us see how data is organized and stored efficiently. It's fundamental to managing and retrieving information effectively in any information system. Now, let's talk about a way to store employee records sequentially using an ID number. This method is quite straightforward. Think of it as lining up the records one after another in the order of their IDs. It's simple and inexpensive, making it a popular choice when budget is a concern. However, it's important to remember that retrieving specific data can be a bit of a challenge with this setup. Since the records are in sequence, finding one particular record might require searching through a lot of data before reaching the right one. This brings us to the concept of file structure, which is essentially about how we decide to store these records on magnetic media like a hard drive or tape. The way we organize the data impacts how efficiently we can access and manage it. In this context, the sequential file structure is one of the basic methods. It's cost-effective and simple, but may not be the best choice when quick data retrieval is a priority. Understanding these options helps us make informed decisions based on our specific needs, whether it's cost, speed, or ease of management. Another way to store records is to keep them randomly, which means we can access data directly from storage devices. This approach makes retrieval easy and quick because you can go straight to the data you need without having to go through other records. But it's important to keep in mind that sometimes, using multiple storage locations can slow down the system. When we talk about direct file structure, we're focusing on how data is organized to enable this kind of efficient access, which ties back to our overall goal of optimizing data management for better performance. Now, let's look at the third way to store records, which is using a direct access medium in a sequential manner. In this method, an index is maintained as records are added to the file, allowing us to quickly locate specific records. This approach is known as the Indexed Sequential Access Method, or ISAM. However, it's important to remember that indexed files require ongoing maintenance of these indexes, which can add overhead. While this system can be very efficient for quick access to records, it can also lead to slower performance in certain situations, especially if the indexes become large or need frequent updates. Overall, this method balances the benefits of direct access with the need for maintaining additional data structures, making it a key concept in understanding different file storage techniques. Now, let's talk about the various ways we can interact with records in a file. First, you might need to modify records. That is, update existing information to keep data current. Creating reports from records is also essential, as it allows us to analyze and present data in a meaningful way. Deleting records becomes necessary when information is outdated or no longer relevant. Viewing records helps us quickly access and review the data stored within a file. And of course, adding new records is fundamental for keeping our data comprehensive and up to date. For organizations or managers, the key point is that they need efficient ways to access these records. Whether it's updating, creating reports, deleting, viewing, or adding, having direct access to records ensures smooth operations and informed decision-making. All these actions, modifying, creating reports, deleting, viewing, and adding, are critical components of effective data management, which ultimately supports the overall goals of the organization. Now, let's move on to the next point about the ID method. As I mentioned earlier, it primarily uses a primary key to locate and identify stored data efficiently. But what's really interesting is the role of secondary keys. These are used to create secondary indexes, which we often refer to as inverted keys. Now, these inverted keys are crucial because they allow us to quickly find data based on attributes other than the primary key. Think of them as an additional map that points us to the data we need, even if we don't have the main identifier. This brings us to inverted files, which are essentially the implementation of these secondary indexes. They help us organize and access data more efficiently by keeping track of which secondary keys are associated with which data entries. Connecting this to our overall theme, understanding these indexing methods, primary and secondary, is vital because they significantly improve data retrieval speeds and system performance. So, inverted files are a key part of making that possible. Now, let's talk about linked lists. The set of data that the pointer retrieves during a search for records is called a linked list. Essentially, it's a chain of data elements connected through pointers. The way we store these records plays a crucial role in how quickly and efficiently we can access or retrieve the data. Different storage methods impact performance, especially when dealing with large amounts of information. Understanding linked lists helps us see how data organization affects overall system efficiency and retrieval speed. This concept ties into the broader theme of data management and optimization techniques we're exploring today. File structures are not just about how data or records are stored. They also significantly influence how we access and process that data. When we talk about file structures, we're really looking at the organization of data within a system. This organization impacts the speed and efficiency of data retrieval, which is crucial for system performance. For example, some structures allow quick access to specific records, while others may be better suited for sequential processing. Understanding these differences helps us choose the right structure for our needs. Ultimately, the way we organize our data affects not only how easily we can find and access information, but also how smoothly our processing tasks run. So, in essence, file structures are foundational to both data access and the overall efficiency of data processing in any system. Let's take a closer look at how file structures are used in batch processing. Sequential access file structure is quite straightforward. It helps in accessing records in a batch of files one after another, and typically, the entire batch is processed from start to finish. This approach works well when you need to handle large volumes of data in a sequential manner. It's important to choose the right file structure based on your processing requirements. Now, shifting gears to real-time processing. This is where things get a bit more dynamic. In real-time or online processing, records often need to be accessed directly, without going through the entire batch. For this, we use either indexed sequential structures or direct access structures, which allow us to fetch specific records quickly and efficiently. The key takeaway here is that selecting the appropriate file structure, whether sequential for batch or direct for real-time, can significantly impact the performance and efficiency of your processing system. This ties back to our overall theme of designing systems that are optimized for their specific operational needs. Let's start by looking at the challenge of data updates. When you update data in a file, it doesn't always automatically update related files or records. This can lead to data inconsistency, which is a big concern because it means different parts of your data might not match or reflect the latest information. Moving on, a key concept here is data independence. If there's a lack of data independence, any change made to the format of a record in a file can affect all other files that depend on that format. This tight coupling makes managing and updating data more complicated and error-prone. Now, you'll notice that we often deal with single record type file systems. These are simple structures where each file contains one type of record, which can be straightforward, but also limiting for more complex data needs. Finally, let's talk about databases. A database is essentially a collection of related files, where each file is made up of records. This organization helps manage large amounts of data efficiently, making it easier to access, update, and maintain consistency across the system. All these concepts tie into the overall theme of understanding how data is organized, managed, and kept consistent within information systems. So, when we talk about a DBMS or database management system, what it does is retrieve data from databases and then provide that data to application programs that need it. Essentially, it acts as a bridge between the data stored and the applications that use that data. One of the key strengths of a DBMS is that it allows access to data in a uniform and consistent way. This means that no matter what application is requesting the data, it will be accessed in a standardized manner, making things much more efficient and reliable. It also organizes data into records in a consistent way. So, instead of everything being jumbled or scattered, the data is structured in a predictable pattern, which simplifies retrieval and management. Furthermore, the DBMS stores data in a uniform and consistent way as well. This consistency is crucial because it ensures data integrity and makes maintenance much easier. At its core, a DBMS is a collection of software programs that work together to manage this data effectively. By doing so, they help organizations handle large volumes of data with ease, ensuring that data is accurate, accessible, and secure. This overall functionality highlights how vital a DBMS is in managing data efficiently within any modern information system. All right, let's take a closer look at the diagram illustrating the process of a DBMS. As you can see, it starts with the application program, which is essentially the interface that users or other systems interact with. This application sends requests to the database management system, or DBMS, which acts as the intermediary. The DBMS then processes these requests, managing the data stored in the database. Finally, the database itself holds all the data that the application needs to access or modify. This flow highlights how the application and database are connected through the DBMS, ensuring data is managed efficiently and securely. It's like a well-organized pipeline that enables smooth communication between users and the stored information, which is fundamental to understanding how database systems support various applications in real-world scenarios. Organizations mostly purchase database management systems software from vendors, and that's because vendors provide ready-made solutions that are reliable and tested. Now, when we look at the components of a DBMS, it's helpful to understand what makes up this complex system. Essentially, A DBMS is built from several key parts that work together seamlessly. These components ensure the system can store, manage, and retrieve data efficiently. As we explore these parts, keep in mind that they all contribute to the overall goal of making data management easier and more effective for organizations. So, understanding these components helps us appreciate the power and flexibility a well-designed DBMS offers. Now, let's take a closer look at the data dictionary or directory. This slide contains the names and descriptions of every data element within our database. For example, you'll see entries like SDOCKNUM, which refers to the number of inventory items. Each data element is clearly defined so that anyone working with the database understands exactly what each piece of data represents. By having this organized reference, we ensure consistency and clarity across all users and systems. This is a crucial part of our overall data management strategy because it helps us maintain data integrity and makes future updates or audits much more straightforward. Essentially, this data dictionary acts as a reliable roadmap, guiding us through the structure and meaning of our data. Now, let's talk about how programmers work with data. They use a special language called Data Description Language, or DDL for short. This language is used consistently across different systems to describe the characteristics of data elements precisely. For example, when they want to find, get, or insert data, they rely on commands that are part of this language. Think of DDL as a clear and standardized way to tell the system what kind of data we're dealing with, its format, and how it should be handled. This consistency helps ensure that everyone understands the data the same way, which is crucial for reliable data management. So, in essence, DDL acts as the backbone for defining and describing data across various operations, keeping everything organized and clear. This slide introduces a communication software package that plays a crucial role in managing the flow of information between the database and remote terminals. Essentially, it enables smooth communication. For example, when customer orders are processed at a branch or store and then sent back to the main database located at headquarters. This ensures that data is consistently updated and accessible across locations. We also see a mention of teleprocessing monitors, which are key components in this setup. These monitors oversee and control the communication process, making sure everything runs efficiently and reliably. Understanding this system is important because it highlights how businesses can manage distributed operations seamlessly. It's a perfect example of how communication software supports real-time data exchange, ultimately improving service delivery and operational accuracy. This ties into our overall theme of how technology integrates and streamlines business processes. This is a program designed to help programmers develop application programs that use the database. For example, these are often referred to as CASE tools, which stands for Computer-Aided Software Engineering. Essentially, these application development tools streamline the process of creating software that interacts with databases, making it more efficient and less error-prone. They provide a set of automated features that assist in designing, coding, and testing applications. Highlighting these tools is important because they support the overall goal of building reliable, scalable, and maintainable database applications. By integrating these tools into our development process, we can improve productivity and ensure consistency across projects. This ties back to our broader theme of leveraging technology to simplify complex tasks and enhance our capabilities as developers. Security software plays a crucial role in protecting our databases. It offers a variety of tools designed to shield sensitive information from unauthorized access. This means that only trusted users can reach the data they need, helping to prevent data breaches. Additionally, security software also scans for and blocks viruses or malware that could harm the database or compromise its integrity. By using these tools, we ensure that our data remains safe, secure, and reliable. This is a vital part of our overall data management strategy, helping us maintain trust and compliance. Now, let's talk about making copies of data and storing them safely. This is where backup systems come into play. They include tools used to restart the database and recover lost data if something goes wrong. These restart and recovery systems are essential because they help us quickly get back on track after a failure. Additionally, we have database managers with tools designed to make copies of the entire database. This is crucial in case the original records are damaged or destroyed. Having those backups means we can restore the data without losing valuable information. All of these components, archiving programs, backup, and recovery systems, work together to ensure data integrity and availability. They are vital for maintaining trust in our data management processes and supporting the overall theme of data security and resilience. When considering the design of output requirements, it's essential to focus on what the end user needs from the reports. This means understanding their specific goals, what information they require, and how they prefer to receive it. Report writers play a crucial role here because they are the ones who translate these needs into clear, effective reports. They need to ensure that the output not only delivers accurate data, but is also easy to interpret and actionable. Ultimately, designing these requirements thoughtfully helps us create reports that truly support decision-making and align with the overall objectives of the project or organization. Now, let's look at how QBE queries work. Unlike traditional SQL, QBE queries don't require a formal statement. Instead, you can use any text or even pictures to define what data you want. For example, if I wanted to list all customers in India along with their names and addresses, I could just input a simple natural language question like, "List the names and addresses of all customers in India." The system then translates that into a query, such as select name, address, city from customer where country equals in. This approach makes querying more intuitive and accessible, especially for users who aren't familiar with complex coding. It's part of a broader set of tools that include SQL, which is a structured language for managing databases, and NLQ, which allows for natural language questions. Together, these tools form a powerful query language ecosystem. QBE, in particular, stands out because it simplifies the process. No need for detailed statements, just natural input. This flexibility is key to making data access more user-friendly and integrated into various workflows. Some vendors offer DBMS software that is designed to work across many different hardware and operating system platforms. This means that if you're using different types of computers or operating systems in your environment, you can still run the same database management system without needing separate versions for each platform. This concept is often referred to as multiple platform databases. It's a really important feature because it provides much greater flexibility and compatibility, allowing organizations to choose the best hardware and OS for their needs without worrying about database compatibility. Overall, this capability supports a more versatile and adaptable approach to managing data across diverse IT environments. Vendors offer integrated www server software combined with a database management system, or DBMS. This integration transforms a standard computer system that hosts a database into a fully functional web server. What this means is that users with web connectivity can access and interact with the database remotely. The key point here is that such software simplifies the process of making databases available online, enabling seamless web-based access. This capability is crucial in today's interconnected world, as it supports the overall theme of integrating data systems with web technologies to enhance accessibility and functionality. So, essentially, this integration turns your database hosting system into a web server, opening up new possibilities for remote data management and user access. Now, as database management systems have evolved, they've actually driven some significant changes within organizations. One of the most important shifts has been the creation of new roles, particularly the position of the database administrator. This person plays a crucial role in ensuring that data remains consistent and secure across the organization. Essentially, the database administrator is responsible for maintaining the integrity of the data, making sure everything is accurate and reliable. They also oversee security measures to protect sensitive information from unauthorized access or breaches. So, their role is vital in supporting the overall data strategy, and ensuring that the company's data assets are well managed and trustworthy. This change highlights how technological advancements often lead to new organizational structures and responsibilities, aligning with our broader theme of adapting to innovation in information systems. Now, let's take a closer look at how records are actually organized and stored on the storage media. This is what we call the physical view. It's essentially the way data is physically arranged on the storage devices, which is often quite different from how users perceive it. On the other hand, how users perceive records in the database is referred to as the logical view. This is more about how the data appears to us, the way we interact with it, and how it makes sense within the database system. Within the database, data has two main views. The first is the logical view, which explains how each data element relates to other data elements. Think of this as the blueprint or the map of how everything connects and interacts. The second is metadata, which includes details like employee names, job titles, or other descriptive information about the data. Think of metadata as the data about the data. It's crucial for understanding and managing the actual data effectively. And speaking of actual data, any database contains two types. It's important to distinguish between them. One is the view of data, which is what users see and interact with directly. The other is the underlying physical data stored on the media, which supports the entire system behind the scenes. Understanding these different perspectives helps us appreciate how databases function both behind the scenes and for the end user, ensuring data is stored efficiently and accessed in a meaningful way. A subsystem is essentially a less comprehensive logical view of the database. It's the perspective that an application programmer, an application program, or even a user might have when interacting with the database. Think of it as a simplified or focused view that helps different users or programs work efficiently without getting overwhelmed by the full complexity of the entire database. Now, moving on to schemas. These are descriptions of the logical view of a database. They serve as the blueprint, outlining how data is organized and related. A common tool we use to design these schemas is the Entity Relationship Diagram, or ER diagram. These diagrams visually map out entities, their attributes, and relationships, making it easier to understand and communicate the structure of the database. So, in the bigger picture, understanding subsystems and schemas helps us manage complexity. They allow different users and programs to interact with the database at the appropriate level of detail, ensuring clarity and efficiency in database design and usage. Now, let's look at some common examples of database approaches, or what we call database models. Think about databases like the employee database, payroll database, or manpower database. These are structured ways of organizing data for different organizational needs. The key idea here is that data in one record often needs to relate to data in another record. For example, an employee's details might be linked to their payroll information. However, as organizations grow larger, finding and managing these relationships can become quite complex. That's where database models come into play. They provide a systematic way to structure and manage this interconnected data efficiently. Understanding these models is crucial because they form the foundation of how we store, retrieve, and manage organizational data effectively. Now, moving on to slide 31, let's look at the different types of database models. There are four main types that are commonly used. First, we have the hierarchical database model, which organizes data in a tree-like structure, making it easy to navigate but less flexible when it comes to complex relationships. Next is the network database model, which allows more complex relationships using a graph structure, enabling multiple connections between data points. Then, there's the object-oriented database model, which integrates object-oriented programming principles, making it ideal for handling multimedia and complex data types. Lastly, we have the relational database model, which organizes data into tables with rows and columns, allowing for powerful querying capabilities and flexibility. These models form the foundation of how databases are structured and managed, and choosing the right one depends on the specific needs of the application. This overview helps us understand the evolution and diversity of database design, aligning with our overall goal of mastering data management concepts. Now, let's take a look at how records are organized in a hierarchical database model. Essentially, records are structured into a hierarchy of relationships, which we often refer to as parent and child relationships. A parent record can have many child records associated with it, creating a one-to-many relationship. However, it's important to note that each child record has only one parent record, which helps maintain a clear and organized structure. This setup is quite intuitive because it mirrors real-world relationships, like a company with multiple departments or a family tree. It's a powerful way to organize data when relationships are naturally hierarchical. Understanding this model is crucial because it highlights how data can be efficiently stored and retrieved in systems where such relationships are common. It ties into the broader theme of data organization and management, helping us see how different models serve different needs. Now, let's look at the network database model. This model is actually more advanced than the hierarchical one we discussed earlier. Instead of a simple tree structure, it allows a set of records to form a network with other sets of records. What this means is that records can have multiple relationships, creating a flexible and interconnected structure. This model enables complex data relationships to be represented more naturally, which is especially useful for certain types of applications. Throughout this presentation, we've seen how different models serve different needs, and the network model offers a powerful way to handle more intricate data relationships efficiently. So this slide introduces the relational database model, which is organized into a series of two-dimensional tables. These tables are designed to make data easy to access and understand. When you look at a relational database, you'll see that data is stored in rows and columns, much like a spreadsheet. The key point here is that this structure allows for straightforward retrieval of information because each record is clearly organized. For example, in the table shown, you can see different records labeled R1 through R4, with columns R5, R6, and R7 holding specific data points. Notice how the records are easy to read and interpret. This simplicity is one of the main strengths of the relational model. It supports efficient data management, making it easier to find, update, and analyze information. Connecting this back to our overall theme, the relational database model is fundamental because it provides a clear, organized way to handle complex data sets, enabling better decision-making, data integrity, and scalability. So, at the core of the object-oriented database model, each object is essentially self-contained. It's bound together with its own data and a set of instructions that describe its behavior and attributes. Think of it like a small, independent unit that knows everything it needs to about itself. Objects that share the same set of attributes and methods are grouped into what we call a class. This grouping helps us organize and manage similar objects more efficiently. Now, these objects don't just exist in isolation. They interact with each other through messages. This messaging system allows objects to communicate and work together seamlessly, which is a key aspect of the object-oriented approach. Finally, each object is described by a set of attributes, properties that define its state and characteristics. All these points tie into the overall theme of how object-oriented databases mirror real-world entities and their interactions, making data modeling more intuitive and aligned with how we perceive the world around us. On this slide, we see several key advantages of using a database management system. First, it leads to improved data administration and control, meaning that managing and overseeing data becomes more streamlined and efficient. This control helps ensure data accuracy and security. Next, there's improved data consistency. When data is managed centrally, the chances of having conflicting or outdated information across different parts of the system are greatly reduced. This consistency is crucial for making reliable decisions. We also see an increased emphasis on data as a resource. Recognizing data as a valuable asset encourages better data management practices and more strategic use of information. Another important point is increased application programmer and user productivity. With a DBMS, developers and users spend less time on data management tasks and more on their core responsibilities, boosting overall efficiency. Data redundancy, which is when the same data is stored multiple times unnecessarily, is significantly reduced with a DBMS. This not only saves storage space, but also lowers the risk of inconsistencies. Additionally, database systems keep the description of data separate from the applications, which is known as data independence. This separation makes it easier to modify data structures without affecting the applications that use the data. Finally, data sharing becomes much easier and more accessible. Multiple users and applications can access and share data seamlessly, fostering collaboration and ensuring everyone works with the most current information. All these advantages collectively demonstrate how a DBMS enhances data management, making systems more efficient, reliable, and adaptable to the needs of modern organizations. Now, let's take a look at some of the common problems faced by database systems. First, security issues are a major concern. Databases must be protected from unauthorized access to ensure that sensitive data remains confidential and secure. We need robust security measures to prevent breaches and data theft. Next, there are resource problems. Running a database often requires extra computing resources, such as processing power, memory, and storage. These demands can impact overall system performance and require careful management to maintain efficiency. Finally, we have concurrency problems. Since multiple users often access the database simultaneously, managing these concurrent operations can be tricky. Without proper handling, this can lead to conflicts, data inconsistency, or even system crashes. All these issues highlight the importance of designing and maintaining secure, resource-efficient, and reliable database systems. Addressing these challenges is key to ensuring our databases function smoothly and securely, supporting the overall goals of our information management. Now, let's talk about query processing. This is the process where a high-level query, like SQL, gets transformed into a correct and efficient execution plan. Think of it as translating a human-readable request into detailed, low-level instructions that the database can understand and execute smoothly. It involves retrieving data and manipulating it as needed to produce the desired result. The query processor plays a crucial role here, selecting the most appropriate plan to respond to the query effectively. Ultimately, SQL query processing requires the database management system, or DBMS, to identify the best strategy for retrieving the data and executing the query efficiently. This step is fundamental because it directly impacts the performance and accuracy of the database system, tying back to our overall focus on optimizing data management processes. Now, let's take a closer look at the second step in query processing, which is query decomposition. This is a crucial phase where high-level queries, like those written in SQL, are broken down into more detailed, machine-level queries that the database can actually understand and execute. Think of it as translating a human language into a language that the database engine can process efficiently. Moving on to the first step, syntax analysis. At this stage, the system checks the SQL query for any syntax errors. This is like proofreading a sentence for grammatical mistakes before it's sent off for execution. Ensuring the syntax is correct is fundamental because it helps prevent errors later in the process and guarantees that the query is valid. Both of these steps, query decomposition and syntax analysis, are integral parts of the overall query processing cycle. They serve as the foundation for transforming a simple, high-level request into a precise, executable set of instructions. This process highlights how the database management system intelligently interprets and prepares user queries for efficient execution. Let's walk through the key stages in query processing as shown in this diagram. First, we start with the query itself, which is written in a high-level query language. From there, the query goes through several important steps to ensure efficient execution. One of the first steps is query analysis, where the system understands what the query is asking for. Then, semantic analysis checks for meaningfulness and correctness of the query's content. Next, query restructuring reorganizes the query to optimize performance and clarity. Following that, the query decomposer works in 5 stages to break down the query into manageable parts. This is where the query simplifier, normalization, and code generation happen, making the query easier to process. The query optimizer then plays a crucial role by choosing the most efficient execution strategy, which can significantly impact performance. This involves query restructuring again to fine-tune the execution plan. All these processes feed into the runtime database processor, which executes the optimized query plan. Throughout this entire process, the goal is to transform a high-level, human-readable query into an efficient, executable set of instructions for the database. This diagram effectively illustrates how each component works together to turn a simple query into a fast, optimized operation. It highlights the complexity and sophistication behind what seems like a straightforward request for data. Let's talk about SQL, which is actually the international standard language used for creating and manipulating relational databases. It's a specially designed programming language, tailored specifically for managing data stored in relational database management systems, or RDBMS. The key point here is that SQL isn't just a random language. It's a universal standard, meaning it's recognized and used worldwide. This makes it incredibly important for ensuring consistency and interoperability across different database systems. As we move forward in this presentation, you'll see how essential SQL is for efficiently working with data, whether you're creating new databases or extracting and updating information. It's the backbone of modern data management. Now, let's take a closer look at some common SQL data types. First up, we have float, which is used for approximate numeric values and is typically used when you need to handle real numbers with decimal points. The P in parentheses indicates precision, but it's optional depending on your specific needs. Next, we see decimal, which is also for exact numeric values with decimal points, and it requires specifying both P and Q, where P is the total number of digits, and Q is the number of digits after the decimal point. Moving on, we have bit, which stores binary data, essentially a series of zeros and ones. SMALLINT is a type for small integers, useful when you want to save space and your numbers are within a limited range. Then there's numeric, similar to decimal, allowing for precise decimal numbers with specified precision and scale. Integer is straightforward. It's used for whole numbers without decimal points, perfect for counts or IDs. Character varying, often written as VARCHAR, allows you to store variable-length character strings, with a maximum length defined by n. Similarly, bit varying is for variable-length binary data, also with a maximum length. Lastly, character or char is for fixed-length character strings, where n specifies the length. All these data types are fundamental because they enable us to define exactly what kind of data we are working with, making our databases both efficient and meaningful. Understanding these types helps us choose the right one for each specific scenario, which is essential in designing effective database systems. Let's take a closer look at transaction control statements, or TCS, which are essential for managing how transactions are handled in a database. These commands help us control the commit and rollback of transactions, ensuring data integrity and consistency throughout our operations. Next, we have data manipulation language, or DML, which includes commands like insert, update, delete, and merge. These are the core commands we use to manipulate data within our tables, making sure we can add, modify, or remove data as needed. Moving on, data query language, or DQL, primarily involves the select statement. This is what allows us to retrieve and view data from the database. It's fundamental because it enables us to ask questions and get the information we need. Then there's data control language, or DCL. Commands like grant and revoke fall under this category, and they're crucial for managing permissions and security within the database, controlling who can access or modify data. Next, we have Data Administration Statements, or DAS, which deal with the administration and management of database objects and resources. These commands help maintain the database environment and ensure everything runs smoothly. Lastly, Data Definition Language, or DDL, includes commands such as create, alter, and drop. These are used to define and modify the structure of database objects like tables, indexes, and schemas. Together, these categories of SQL commands form the toolkit that allows us to perform simple to complex tasks against data inside a database. They're central to interacting with and managing data effectively in any database system. Let's take a closer look at some key data definition language commands that are essential for managing database structures. First, we have the drop table command. This command is used to remove an entire table from the database. Once you execute drop table on a table, it's gone forever, meaning it can't be recovered, so use it carefully. For example, if you want to delete a table named employee, you would write drop table employee. Next, we have alter table, which allows us to modify the structure of an existing table. For instance, if you need to add a new column, such as a telephone number, you would use alter table followed by the table name, then ADD, the column name, data type, and any constraints if necessary. This command is very useful when you need to update your database schema without recreating the entire table. Finally, we have create table, which is used to create new tables to store data. You specify the table name and define each column along with its data type. For example, creating an employee table with columns for employee code, name, and gender. This command forms the foundation for structuring your database. Overall, these commands, drop table, alter table, and create table, are fundamental for defining and maintaining your database's structure. They give you the power to create, modify, and delete tables as your data needs evolve. Now let's look at how the delete statement works. For example, if we want to remove a specific record from a table, we use the syntax, delete from table name where column name equals some value. This allows us to delete a single record that matches the condition. It's important to include the where clause, otherwise, we might delete all records in the table. Moving on to the update statement, this command is used when we need to modify existing data. For instance, if we want to update the average temperature in a weather table for Madurai, we would write update weather set average temp equals 20 degrees Celsius where city equals Madurai. The syntax involves specifying the table, the columns to change, and the new values with the set keyword. The where clause again helps us target specific rows that need updating. Finally, let's consider inserting new data. The insert into statement allows us two main options. We can insert data by specifying the table and the values directly, like insert into employee values, 15, Srinath, aeronautics. Alternatively, we can specify particular columns and then provide the corresponding values. This flexibility helps us add new records efficiently. Overall, these commands, delete, update, and insert, are fundamental parts of data manipulation language, giving us control over how we manage and modify data within our databases. They are essential tools for maintaining data accuracy and relevance in our systems. Now let's take a closer look at the select statement. This is the core command used to retrieve data from a database table. The basic syntax is straightforward. Select, followed by the column names you want to see, then from, and finally the name of the table. Think of it as asking the database, hey, give me this information from that table. This simple yet powerful command allows users to query one or multiple tables to get exactly the data they need, making it a fundamental part of data retrieval in SQL. Remember, understanding how to craft effective select statements is key to efficiently working with databases. Now, let's talk about some essential commands in data control language that help us manage who can access our data. On this slide, you'll see two key terms, revoke and grant. Grant is used when we want to give a user permission to access certain data or perform specific actions. It's like handing over the keys to a particular resource. Conversely, revoke is used when we need to take those permissions away, ensuring that access is controlled and only authorized users can view or modify the data. These commands are crucial in maintaining data security and integrity, especially in environments where multiple users have different access needs. By using grant and revoke effectively, we can prevent unauthorized access and keep our data safe. This ties into the overall theme of data security, emphasizing how important it is to control access carefully to protect sensitive information. Now, let's look at how we can manage our database operations with a simple yet powerful control. When we select Stop Audit, it halts the ongoing audit processes, essentially pausing the collection and analysis of data. Conversely, Start Audit begins or resumes the audit activities, allowing us to monitor and analyze operations as needed. This control is vital because it gives us flexibility to focus on specific activities or troubleshoot issues without constant overhead. The core purpose of these commands is to enable us to perform detailed audits and analysis on what's happening within the database. By doing so, we can ensure everything is running smoothly, identify anomalies, and maintain security and compliance. A key feature here is the Data Administration Statements, or DAS. These statements are tools that let us manage and control auditing activities directly. They're essential because they give us the ability to tailor our audit processes to fit specific operational needs. Overall, these commands and DAS are about giving us better oversight and control over database operations, making sure we can efficiently monitor, analyze, and respond as needed. It's a critical part of maintaining a healthy, secure, and well-managed database environment. Let's talk about managing changes with transaction control statements, or TCS for short. On this slide, you'll see three key commands: SAVEPOINT, rollback, and commit. These are essential tools for controlling how your database handles changes made by DML statements. A SAVEPOINT lets you set a specific point within a transaction. Think of it as creating a bookmark, so if something goes wrong later, you can roll back to this particular spot instead of undoing everything. Rollback is used when you want to undo all changes made since the last save point or since the start of the transaction. It's like hitting undo for your database operations, restoring it to a previous state. And then there's commit. When you're confident that all your changes are correct and you want to make them permanent, you use commit. This finalizes the transaction, saving your changes permanently to the database. So these commands give you precise control over your data modifications, allowing for safe, reliable, and consistent database operations. They are foundational to transaction management, ensuring data integrity even when errors occur. Now let's talk about some key aggregate functions that are essential when working with data. First up is the max function, which helps us find the largest value in a selected column. It's really useful when you want to identify the highest figure, such as the top sales or maximum score. Conversely, the min function does the opposite. It returns the smallest value in a column, like the lowest sales or minimum measure. Next, we have the count function. This one counts the number of rows in a specific table or dataset, giving us a quick way to see how many records we're dealing with. For example, counting how many orders or customers we have. Lastly, there's the sum function, which adds up all the numeric values in a column. It's perfect for calculating totals, like total revenue or total hours worked. These functions are fundamental because they allow us to analyze and summarize data efficiently, which ties into our overall goal of understanding trends and making informed decisions based on the data. Now, let's take a closer look at some of the disadvantages associated with the use of certain query languages. One challenge is the complexity of the grammar, which can make writing and understanding queries more difficult. There are also issues with misconstructions in the where clause, leading to potential errors or unintended results. Join inconsistencies can occur when combining tables, which can complicate query development. Additionally, vendor variation means that different database systems may implement these features differently, reducing portability and consistency across platforms. On the flip side, there are notable advantages to consider. These languages support object-based programming, making it easier to work with complex data structures. They are interactive, allowing users to experiment and refine queries easily. They are also compatible with any database management system, giving you flexibility in your choice of technology. Plus, they are generally easy to learn and understand, which lowers the barrier to entry for new users. Finally, their portability means that queries and applications can move seamlessly across different systems without major modifications. So, while there are some drawbacks, these languages offer significant benefits that support efficient, flexible, and user-friendly database interactions. Let's talk about parallel concurrency, which is really a key property of systems where multiple computations are happening at the same time. When a database management system is used by more than one user simultaneously, things can get a bit tricky if the system isn't designed properly to handle multiple users. That's where concurrency management comes in. It ensures that these multiple operations can occur smoothly without interfering with each other, maintaining data integrity and consistency. So, understanding how to manage concurrency is crucial for building reliable, multi-user systems that can handle real-world demands efficiently. Let's talk about versioning and locking, which are key strategies in managing concurrency. When multiple users access data simultaneously, conflicts can arise, so we need effective methods to handle that. One approach is locking records, which temporarily restricts access to a specific record to prevent conflicts. This method helps reduce waiting time, making the system more efficient. Similarly, locking data fields targets individual pieces of data within a record, allowing for more granular control. Locking entire files, on the other hand, is a broader approach where the whole file is locked during a transaction, which can be simpler but might also lead to longer wait times. The main goal here is to avoid concurrency issues altogether, and that's why we implement various methods to improve throughput and resource utilization. By managing how data is accessed and modified, we can ensure smoother operations, prevent conflicts, and optimize system performance. This slide ties into our overall theme of effective data management, emphasizing that proper concurrency control is essential for maintaining data integrity and system efficiency. Let's dive into what a data warehouse really is. Essentially, it's a centralized collection of corporate information. This data comes directly from operational systems. Those are the day-to-day applications and processes, and also from some external data sources. The goal here is to gather all relevant information in one place to support better decision-making. Now, a data warehouse isn't just about collecting data. It's designed to be subject-oriented. That means it organizes data around specific topics or areas important to the business, like sales, finance, or customer data. This organization makes it easier to analyze and extract insights. Another key point is that data warehousing is integrated. This integration ensures that data from different sources is consolidated and consistent, providing a unified view. It also tends to be non-volatile, so once data is stored, it doesn't change, which maintains data stability for analysis over time. And finally, it's time variant. This means it keeps historical data, allowing us to analyze trends and patterns over different periods. All these characteristics, subject-oriented, integrated, non-volatile, and time-variant, are what make data warehouses powerful tools for supporting decision-making processes across the organization. Let's take a closer look at some of the key features of data warehousing. First, non-volatility. This means that once data is stored in the warehouse, it doesn't change or get deleted easily. It's stable, allowing us to analyze historical data without worries about it being overwritten. Next up is integrity. Ensuring data integrity is crucial because it guarantees that the data we work with is accurate and reliable. This trustworthiness is essential for making sound business decisions based on the data stored. Moving on, we see that data in a warehouse is time variant. This means that data is stored with a timestamp or over different periods, enabling us to track changes over time and analyze trends effectively. Finally, subject-oriented. Data warehousing is organized around specific subjects or areas of interest, like sales, customers, or products. This focus helps us analyze data more meaningfully and supports decision-making tailored to particular business functions. Together, these features, non-volatility, integrity, time-variant, and subject-oriented, are what make data warehousing such a powerful tool for consolidating and analyzing large amounts of data efficiently and reliably. Now, let's take a closer look at the architecture and structure of a data warehouse, specifically the three-tier model. At the top, we have reporting, analysis, and data mining tools. These are the interfaces and applications that end users and analysts use to extract insights, generate reports, and perform complex data analysis. They're the tools that help us turn raw data into actionable information. Moving down to the middle tier, we find the analytical processing layer. This is where online analytical processing, or OLAP, systems operate. They enable us to perform multidimensional analysis, quickly drill down into data, and uncover trends or patterns. This layer is crucial for supporting complex queries and swift data exploration. Below that, at the bottom tier, is the transaction processing layer. This is where the actual data is collected and processed in real-time or batch modes. It handles the day-to-day operations and ensures data integrity before it moves up into the warehouse. Finally, all of these layers sit on the data warehouse itself, which forms the foundation of the entire structure. The data warehouse consolidates data from various sources, organized in a way that supports efficient querying and analysis. This three-tier architecture is fundamental because it separates different functions: transaction processing, analytical processing, and user interaction, making the system more scalable, flexible, and easier to manage. Understanding this layered approach helps us appreciate how data flows through the system, from raw transactions all the way to insightful reports and analyses, aligning perfectly with our overall goal of effective data management and decision-making. Now, let's look at the key components that make up a data warehouse. First, we have the information delivery system, which is essentially how we provide data insights to users. Then, there's the data warehouse administration and management, ensuring everything runs smoothly and efficiently. Data marts are specialized subsets of data tailored to specific business areas, making analysis more focused and manageable. Data mining plays a crucial role here, as it allows us to discover hidden patterns and relationships within the data. Online analytical processing, or OLAP, enables fast, multidimensional analysis, so users can explore data from different angles quickly. Applications refer to the various ways organizations utilize these data warehouse components to support decision-making. Access tools are vital for interacting with the data. They help us accommodate changes in source data definitions, establish defaults for missing data, and calculate summaries or derived data to enhance analysis. They also convert data to common names and identifiers, ensuring consistency, and remove unwanted data that may not be relevant or accurate. On the other hand, sourcing, acquisition, cleanup, and transforming tools handle the initial stages, bringing in data from various sources, cleaning it up, and transforming it into a usable format. Moving on, the data that describes the data warehouse itself is called metadata. Metadata is essential because it provides context, helping users and systems understand the structure, content, and rules associated with the data. Finally, the core of the data warehouse is the database itself. Today, many warehouses rely on a multidimensional database, which uses a new index structure to bypass traditional relational tables, allowing for faster querying. Some also leverage parallel relational database designs to enhance performance and scalability. All these components work together seamlessly to support complex data analysis, ensuring that organizations can make informed, data-driven decisions efficiently. Now, let's talk about data marts. Essentially, Data marts are smaller, specialized sections of the larger data warehouse. Think of them as partitions or segments that focus on specific areas or departments within an organization. Their main goal is to make it as easy as possible for users to access the information they need quickly and efficiently. This targeted approach helps streamline data retrieval and supports quicker decision-making. By providing these focused data subsets, data marts align with the overall theme of data management, making data accessible and usable. They serve as a bridge between the massive, complex data warehouse and the end users who need relevant insights without getting overwhelmed. So, in essence, data marts simplify access and improve efficiency, helping organizations get the insights they need when they need them. Let's talk about data marts and their characteristics. First, it's important to understand that there is no uniformity in data marts. Each one can be quite different depending on the needs and design choices. They typically contain only a small part of an organization's data, focusing on specific departmental or functional areas. An organization can have multiple data marts, and these can be built using different designs, which adds to their flexibility. One of the main advantages of data marts is that they are relatively easy to design, build, and test, making them a practical solution for quick deployment. Because of this simplicity, an organization can independently build many data marts without needing to overhaul existing systems. The source of a data mart can vary. It might originate from a data warehouse, another data mart, or even an OLTP system, which handles daily transactional data. In contrast, a data warehouse typically spans the entire organization and is designed using an enterprise data model, which helps ensure consistency and integration across the organization. Building a data warehouse is a significant project that requires careful planning and substantial resources. Finally, the main goal of a data mart is to meet the specific needs of a department or business unit. They are tailored to support particular analytical or reporting requirements, making them a valuable component of an overall data strategy. And with that, we come to the end of our journey through data warehousing concepts. Now, let's briefly touch on relational OLAP or ROLAP. ROLAP uses relational databases to store and manage multidimensional data, allowing for flexible querying and scalability. It's a good fit when dealing with large, complex datasets that require detailed analysis. Moving on, I want to highlight the concept of data marts. A data mart is essentially a smaller, more focused version of a data warehouse. It's designed to serve specific business lines or departments, making data more accessible and tailored to particular needs. Finally, when we talk about types of data marts, we're referring to their different structures and deployment methods. These can include dependent data marts, which rely on an overarching data warehouse, or independent data marts, which are standalone. Choosing the right type depends on your organization's data strategy and requirements. And that wraps up our presentation. Thank you for your attention, and I hope you've gained a clear understanding of these key data warehousing concepts.